All right. Let's first talk about what's coming up. We have a quiz at the end of class today. This week is lab exam 3. And then regular exam 3 is next Wednesday. That would be December. It's impossible to know. December 6th. Oh. And the topics for that are going to be everything before rotational kinematics. So no rotational stuff on this exam, but there will be on the final. So the last stuff on this exam is going to be conservation laws. So no rotational motion. And then I guess I can figure out when our final is. We meet Mondays and Wednesdays at 12. Mondays and Wednesdays at 12. So our final is Monday, the first day of finals week at 11. Okay? Anybody have any questions about the stuff coming up?
What's the date, the 11th?
Yes. Does anyone have any homework questions you want me to go over? What I'm planning to do today is just, I'll do an example problem to get you back in the thinking about rotational kinetics. And then I'm going to write up some problems and have you do some problems and do some different types of examples and stuff like that. Just so today, hopefully, I'll just give you some more familiarity with this stuff. Okay, so here's the first one. Let's say we have this object that's 3 meters long. And we're applying a force to it down here of 100 newtons. And let's say we also apply a force here of 60 newtons. The mass of this thing is 20 kilograms. What's the angular acceleration? And I'm assuming that this is hanging from the ceiling, so down is this way, so gravity's acting toward the bottom of the page. Well, I like to just go through the same steps every time. I think it helps keep you from forgetting stuff. So I'm going to start out by calculating the moment of inertia, and then I'll do the free body diagram and go from there. So the mass moment of inertia, notice I didn't give a thickness for this. If you're not given the thickness, do you remember what I said?
You don't.
Yeah, just treat it as 0, yeah. Because if the length is a lot bigger than the width, then the width is going to contribute basically nothing to the moment of inertia because you're squaring the differences in those lengths. So the mass moment of inertia, this is the hinge. And so this is 1/3 times the mass times the length squared plus, 1/12 times the mass times 0 squared. So this part just goes away. And you get, I believe that's 60 kilogram meters squared. And now I'm going to draw a free body diagram. Okay, well, there's a weight force at the center. I'm just going to extend it out like this so you can see it better. That's 20 times 9.81, so 196.2. There are unknown force components at the hinge. I'll call that Rx and Ry. Who remembers what the moment is that these are going to produce?
What do you mean?
So these two forces, Rx and Ry, remember, so to calculate the moment, when we calculate the moment, we're going to multiply the force times the distance, that perpendicular distance from the force to the point. So anything that happens at the hinge doesn't produce a moment. So that's, even though those are real forces, and we could calculate what they are, I'll do that at the end, they're not gonna produce a moment for the rotational equation. And then we have 100 newtons this way, and 60 newtons this way. And now let's go through and just calculate all the moments one by one, using the hinge as the about point. So that's what you're always going to do, is whatever point fixes this body to the ground or the ceiling or wall or whatever, that's going to be the about point. Okay, so the easy one is the moment produced by those forces R is 0. Now let's think about the weight force. I'm going to draw it here so it's easier to visualize the line of action. Okay, well, the line that goes from the hinge to where that weight force is applied, the middle, is not perpendicular to that force, right? So we have to move this force along its line of action until they are perpendicular. And what you see is that this weight force, its line of action goes right through the about point. And so that means that there's 0 moment. Okay. So we have 196 plus or minus 196.2 times 0, because the line of action goes through the hinge. So this is also 0. Now the 60 Newton force. That's plus or minus 60 times, what's the distance from the hinge to that 60 Newton force?
1.
Yep, 1.5. And if you ignore all the other forces, would that 60 make it rotate clockwise or counterclockwise? Clockwise, and so we want the negative, and so this is negative 90 Newton meters. And now the 100, that's plus or minus the force is 100. What's the distance from this line of action to the hinge?
3.
3, yep. And would that make it rotate clockwise or counterclockwise? Counter, yep.
Is it because the way the arrows are facing?
Yes.
Okay.
Yeah, so you just have to visualize, like if you push in that direction, which way would the thing rotate? So this is positive 300 Newton meters. And now we've dealt with every one of those forces. So now we'll go to the rotational Newton's second law. And we get that 0 plus 0 minus 90 plus 300 is equal to the moment of inertia, 60, times the angular acceleration. So we get positive 210 is equal to 60 alpha. And so alpha is positive 3.5 radians per second squared. Any questions about that? Okay, well, the forces up here at the hinge, they didn't produce a moment. But you can imagine those are real forces. I mean, it has to, if those forces weren't there, this thing would just fall down to the ground. So how could we calculate the forces Rx and Ry? For that, we can use Newton's second law. Okay, so so for part B, let's say that at the instant these forces are applied, the angular velocity of this body is 0. That's not something we can calculate. We can only calculate angular acceleration. So that has to be given if you're going to do this. Okay. So what we're going to do is calculate the acceleration of the center of mass. So Newton's second law says F net is equal to the mass of the body times the acceleration vector of the center of mass. So we have to calculate the acceleration of the center of mass, and then we can calculate those forces. Okay? All right, so what's the acceleration of the center of mass of this body? Well, it's following a circular path like this. The path of every point is a circle around the hinge or around the about point. Okay? We calculated that the angular acceleration was positive. So it's rotating counterclockwise, yeah. And so that means if the angular acceleration is counterclockwise, the tangential acceleration is this way. Okay? The centripetal acceleration is this way. And so we're going to figure out the total acceleration of that center point. We calculated the angular acceleration, but now we're going to calculate the actual acceleration of that center point. The translational acceleration, not the angular acceleration. Okay, so the magnitude of the centripetal acceleration is v squared over r. Well, if there's no angular velocity, there's no v, so this is just going to be 0. So if there's no angular velocity, that means there's no speed either. What about the magnitude of the tangential acceleration? That's equal to the absolute value of the angular acceleration times the radius of that circle. The absolute value of the angular acceleration we got was 3.5. What's the distance from the axis, the hinge, to this point that we want? 1.5, yep. And so this is 5.25, I think. We figured out that the tangential acceleration is to the right. That's the positive x direction. So the tangential acceleration is 5.250. And since there's no centripetal acceleration, this is the total acceleration of that point. And so now we can go to Newton's second law and add up all the forces. So we have Rx and Ry. We have the 60 Newton force in the negative x direction. The 100 Newton force in the positive x direction. The weight in the negative y direction, 0, negative 196.2. And all that is equal to the mass, 20 kilograms, times the acceleration of the center of mass, which is 5.250. And now we can just calculate this. So we got Rx minus 60 plus 100 plus 0 is equal to 105. And so Rx is equal to 65. And then the y equation says Ry plus 0 minus 196.2 is equal to 0. So Ry is equal to positive 196.2. And so all this says that the force on the bar by the hinge is 65, 196.2. I'm not going to make you do problems like all this stuff, but I just wanted you to see how, I mean, it's not too much of a stretch to imagine how you could think through this, you know. But the thing you will have to do is to this point. Okay. Anybody have any questions about that?
What's the difference between the tangential and the angular acceleration?
Yeah. Well, the angular acceleration is its own kind of thing. It's telling you how fast. So remember, angular velocity is how fast the orientation is changing.
Okay.
And angular acceleration is telling you how fast that angular velocity is changing. So it's like sort of a circular thing. It's its own thing. Tangential and centripetal acceleration are those parts of circular motion that we've been talking about for a while now. So those are the things you're used to. Yeah, so that's about the best I can describe it. Any other questions right now? Okay. So like I said, you're just going to be doing problems like part A here, and I'll show you a couple, like you won't be using Newton's second law with this, but I just wanted to show one time how that can come into it. Okay, so let's say that we have a board connected to the wall. And it has a length of 4 meters. We're going to ignore the thickness. And let's say the mass is 10 kilograms. And let's say that there is a force applied this way of 30 newtons. What's the angular acceleration of the board? Okay, so take a few minutes and see if you can work through this. So I would say start out by calculating the moment of inertia. And then calculate the moments for each one of those forces and go to rotational Newton's second law. And after you work on it for a while, I'll go through it so you can compare your steps. All right, so the first thing I'm going to do is calculate this moment of inertia. So we have 1/3 times the mass of 10 times 4 squared, the length squared. And what do you get for that? 53? Like this? Yeah. Kilogram meter squared. And now we'll go to the free body diagram. There's a weight force acting at the middle. That's 10 times 9.81. There's a 30 Newton force at the end. And then there's the unknown forces acting at the hinge, Rx and Ry.
What is Ry? Like, what's the...
Those are the components of the force vector that the brackets of the pin is applying to that body.
Oh, so like where the hinges?
Right. Yep. It's the force the hinge is applying to the body. And so if that wasn't there, it would just detach from the hinge. Yep. Okay, so the moment due to those forces at the hinge are 0, like always. The moment for the weight is plus or minus the force of 98.1 times the distance from the hinge to that point, which is 2. Would that weight force make it rotate clockwise or counterclockwise around that hinge? Counter, yep, so this is positive, and so you get positive 196.2 Newton meters. And then the 30 Newton force, that's plus or minus. The force is 30. What's the distance to the hinge?
2?
It's 4 this time, yep. And would that upward force of 30 make it rotate clockwise or counterclockwise? Clockwise, yep, so negative. And so we got negative 120 Newton meters. And so the moment equation, the rotational Newton's second law, says 0 plus 196.2 minus 120 is equal to 53.3 repeating times alpha. And so you get 76.2 is equal to 53.3 repeating times alpha. And so what do you get for alpha?
1.42875.
1.48.
228.
428.
So 3.
4.3. I'll call it that. It's positive. And so what we figured out is that it's going to this body is going to have an angular acceleration that's counterclockwise. Does that make sense with what you would expect to happen here? It's a little hard to tell because of this 30 Newton force. It just depends whether that is enough to offset the weight force or not. But the weight force has a bigger moment, and so the effect is that this is going to rotate counterclockwise. Okay? Here's another kind of problem that you'll see sometimes. So let's say we have like a teeter-totter. And let's say we apply a force here of 100 newtons. And we apply a force here of F. We don't know what that is, okay? And the question is, so let's say that this is 1 meter, and this distance is 0.5 meter. What's the value of F that's required to have an angular acceleration of 0? Let's give this thing a mass. Let's say it's 20 kilograms. Okay, well, normally in the problems we've just done, I start by calculating the moment of inertia. But notice that when you go to rotational Newton's second law, where do I have that written? Anywhere? I'll write it here. So you add up all of those moments, and they're equal to the moment of inertia times the angular acceleration. Well, if we're setting the angular acceleration 0, we're looking for the force that makes this 0, we don't even have to bother calculating that moment of inertia because this all goes away. Okay? So I think there's a problem somewhere in the homework where you have sort of this funny shaped thing, and you're like, how do I calculate the moment of inertia of that? And it's a problem like this, so you don't have to, is the answer. Okay? If the angular acceleration is 0, you don't have to calculate the moment of inertia. Okay, so we can go straight to the free body diagram. We have a downward force of 100 here. At the middle, we have a horizontal and an upward force. This is Rx. This is Ry. We also have a weight force. I'm just moving it up here so it's not so cluttered. And that weight force is 196.2. And then we also have here this force F that we're trying to calculate. So now we can calculate the moments for each of these forces. The moment produced by those forces R is 0, like always. The moment due to gravity. Well, what's the distance from the weight force to the hinge? 0, yep. So this one is going to be, plus or minus 196.2 times 0. So that's 0. Then for the 100 Newton force, plus or minus 100. What's the distance from the 100 Newton force to the hinge?
1 meter.
Yep. And would that 100 make it rotate clockwise or counterclockwise? Clockwise, yep. And so this is negative 100 Newton meters. And now the last one is that force F. So plus or minus F. What's the distance from that force F to the hinge? 0.5. And would that downward force F make it rotate clockwise or counterclockwise? Counter, yep. So this comes out to be positive 0.5 times F. And now the moment equation, rotational Newton's second law says 0 minus 100 plus 0.5 F is equal to moment of inertia times alpha. That's 0, remember, because alpha is 0. And so do the algebra, you get 0.5 F is equal to 100. Multiply both sides by 2, and you get that force F has to be 200 newtons for this to not accelerate. Any questions about that? Which probably sort of makes sense to you if you're basically, it's a teeter-totter where you have someone with twice as much weight as the other person. It kind of makes sense that that person would have to be half as far from the center, but we just calculated it. Okay, let's do one like that. So let's say we have a hinge connected to the wall. And the mass of this thing is 30 kilograms. The length is 3 meters. And if we're applying a force upwards at the end, the question is, how big does that force F have to be for this to have no angular acceleration? So what F is required for an angular acceleration equal to 0? Take a few minutes and see if you can work through that. How many people want more time? Anyone? Okay. One thing to just sort of look out for is, I mean, I've given you enough information here to calculate the moment of inertia. This isn't a problem where you need it, but it wouldn't hurt anything if you calculated it. You just see when you went to the equation, like, oh yeah, this is one of the ones where I don't need it, you know? But if you ever have a problem where you're like, I have no idea how to calculate this moment of inertia, consider the possibility that it's a problem where you're looking for acceleration equals 0. And that's why there's no way to calculate moment of inertia, because you don't need it, okay? All right, so we can just skip to the free body diagram. The weight acts at the middle. That is 294.3. At the hinge, we have Rx and Ry. And then over here, we have a force F. The moment produced by those R forces is 0, like always. For the weight force, we have plus or minus 294.3 times the distance from that weight force to the hinge. What's that distance? $1.5. Are you with me on that? And would that weight force make it rotate clockwise or counterclockwise? Yeah, clockwise, so negative. Can someone multiply that for me?
Yeah, I think you get 441.45.
441.45, thanks. And now the force F. So you got plus or minus the force F times, what's the distance from that force to the hinge? 3, yep. And would that be a clockwise or counterclockwise rotation? The F. This is the hinge over here. Counter, yep. So this is 3F. And so now rotational Newton's second law. We have 0 minus 441.45 plus 3F is equal to 0 because alpha is 0. And so 3F is equal to 441.45. Can you divide that by 3? 127 point what?
140.
Oh, 40. Point what?
15.
Okay. 147.15 newtons. Any questions about that? Okay. Well, I think that's enough for today. I'm not feeling so great. Let's just do the quiz and get out of here.